Okay, we're back. It's been pointed out that I didn't mention how to get or install IPython or Jupyter. If you want to use the whole notebook thing, especially if you want to do stuff with scientific Python packages like SciPy, scikit-learn, Numpy, Matplotlib, the scientific Python community has largely adopted something called Conda or Anaconda, which is a package manager for packages that's not Python specific, but is quite popular in the Python community. So if you want to get Jupyter and IPython, if you visit jupyter.org, you can click Install the Notebook, and there are various options. The quickest way to get kind of a full scientific Python environment set up is to get something called Anaconda, which is a Python distribution that contains Python and a whole bunch of scientific Python applications. And it's a full just GUI installer. You just click some buttons, and then you've got Anaconda. And then you'll have Jupyter and IPython and everything. If you just want terminal IPython for, if you like living in the terminal and you just want to use the interactive Python stuff, you can just pip install IPython just like any other package. You can also pip install Jupyter, but that will only get you Jupyter in the notebook, not all the libraries that you use like Matplotlib and everything. So if you're experienced with Python and you like installing things with pip, you can pip install Jupyter or pip install IPython. And if you want to use the wider collection of packages, I'd recommend picking up Conda or Anaconda. And so there's two flavors of Conda. One is called Mini Conda, which is just the Conda package manager, and you can install just the packages you want to use, with like Conda install Jupyter, Conda install Matplotlib, that kind of thing. Or you can get Anaconda, which is the same thing, just with a bunch of packages that they expect are common, like Matplotlib, SciPy, Numpy, Jupyter, IPython, scikit-learn, this kind of thing. And just a minor plug, I highly recommend everybody start with Python 3. It's been more than 10 years. It's time. And actually, the current development version of IPython has dropped support for Python 2. So if you want to keep up with new versions of IPython, you cannot use Python 2 anymore. The current stable version is the last version that will support Python 2. Yeah, and then back to the LIGO stuff I mentioned. So the LIGO experiment, now when they have new results, they post these tutorials, which are notebooks doing signal analysis, downloading the raw data, kind of showing you their process of doing analysis and results, and they just give you little links to open a notebook that actually goes through the analysis on my binder or on Microsoft Azure. And so you can click those links, and then you'll get, so this is running on Binder. It gave me a little notebook, and I can step through the results that kind of load the data, explain how the data works, do some plots of the signal. You can see that's what the LIGO signal looks like. It's simple time series stuff. I can plot deviations in the signal, and then I'd explain some signal processing, kind of all the math and statistics of how they came to their results. You can see spectrograms of the data over time, and so that doesn't look like there's much going on because the signal for these LIGO results is really, really small, so they do a bunch of work to kind of clean things up, and then you can see this is basically the events that they observed, this little sweep here. And then there's a bunch of bandpassing and filtering you can do on the data, and it goes through what all this stuff means. And because it's a wave, whenever there's a wave, you can always hear it. That's what the LIGO event sounds like. Yeah. Right, so that's the kind of thing of you do your science, you actually do everything you did, and then you can publish how you did your analysis and computed results, and other people can say, okay, that's useful. Maybe I'm going to take that and apply it to my own work, or maybe I'm going to say, wait, that doesn't make sense. You got an off by one error here, and your result is totally invalid. So, that both of those can be useful, although one can be a bit embarrassing. So the rest of the time I'm going to spend not explaining IPython itself, but talking about going through an example of doing kind of a real workflow of optimizing and profiling some code using the kinds of things that are that IPython helps you do. So the task we're going to work on is so we're going to do a bit of profiling and optimizing. We start with some time it. So I'm going to just time some dot products so I can just see what's the scaling of the NumPy dot product. You can see it's 87 microseconds when it's 100 square, and then when it's 2,000 square, it's about 80 milliseconds, and then when it's 2,000 square, it's about 0.6 of a second. You can look at time it. As we kind of mentioned before, you can say, show me, do it only instead of 1,000 best of 3. I can do 100. I can do one time, just give me the best out of 100 runs. And then when you do this, the time it result actually gives you an object. So there's a time it result as a thing. If I look at PR, it's a time it result that tells you a bit about how it ran and then about all the samples it took. So you can see the best and worst times. You can see all the runs. There's a list of every value it found. And then we can plot, make a little histogram. These are the timings of the code we just ran. So we can see usually it's in this range of 200 microseconds, but then occasionally it takes a long time. Maybe this was the first run that there was some, we were warming up the cache on the chip or something like that. So the thing that we're going to optimize is diffusing away. So we're going to write an implementation of the diffusion equation in 1D. We start with our input is a sawtooth wave. So we just used SciPy to produce a sawtooth. So we've got t is our time and x is our waveform. And then we're looking at, we can see it, and then this is the math that we use. So this is, we're diffusing the wave by just evolving the heat equation. And then this is our finite difference discretization. So this is just the math of implementing that differential equation numerically using the simplest implementation. And you can see these are just array operations of the next iteration of a point in the array is this smoothing of the previous point, and then taking some averaging of the nearby points to kind of implement the diffusion. So every time step, it diffuses at most one point in our array. So how it diffuses will be a function of how fine our resolution is in the array. So this is a simple, the most straightforward implementation, Python implementation of that diffusion. So we've got our math of the next xk, which we've called y. Could have called it xk probably. And so we make a copy of x, and we've got another array. And our boundary conditions are the initial edges on 0 and n are the same as the previous. So our boundary conditions are fixed. And then we just evolve it a number of steps, so for each time step. And then we iterate over the array and say each item in the array is this smoothing of the item in the previous array with the item to the left and the item to the right. Okay, so this is just our straightforward iterate through the steps, iterate through the array for all the items. And you can see what happens when you, let's actually run that. That's fine. So this is, the dotted line is our input, and the smooth line is what happens after a period of time of diffusion. So now we can use timeit to say, okay, how long did that take? So we take the best value, and then we record that in a list, and we're recording a label because we're going to be doing this a few times. We're going to record, okay, this is the time we took for this particular implementation, and then this is the label we're assigning. So this is our pure Python implementation. It took about 1.3 seconds, which is a bit of a while. So the first thing, if you're working in numerical code in Python, if you're dealing with things like arrays and matrices, you probably want to be using Numpy, because Numpy lets us do something called vectorizing the inner loop. So the inner loop was, we had this, for each item in the array, tell me the value of that item based on the previous one. And Numpy lets us say, in a single operation, say the next array is the previous array with these operations on the previous array. So that's, now I've got one Python statement, and that one Python statement is updating all the elements in the array. We can run it, we can say, yeah, it looks pretty similar. It's actually the same. And then we run the timing, and this time it took 27 milliseconds rather than 1.3 seconds. So that's a pretty big difference. We record our times, and then we can say, okay, how's Numpy doing compared to Python? So this is a log plot of, we got 1.3 seconds for pure Python, and then 30 milliseconds for Numpy. So using Numpy when you can makes a big difference. And let's see, how do we do? Okay, it's about 50 times faster if we just change that one thing, use Numpy instead of lists. And then the optimizing we're going to do is with Cyclone, which I think you've seen before, yeah. And Cyclone provides extra magics for working with Cyclone interactively in IPython. So IPython has this notion of extensions. So we load an extension with this load ext magic, and when you have the Cyclone package includes an extension for IPython. So if you have Cyclone, you have this IPython extension. We just load the Cyclone extension. That's fine. And now we've got this magic Cyclone. So instead of having to write Cyclone pix files and things, we can just put a cell with $Cyclone, and then we can time it. So what this magic did was it actually took that little cell, and then it compiled it with Cyclone, and then imported the resulting function from that compiled module. And then we can write psum. This is our Python sum, just summing all the integers up to a number. And Cyclone-A, this is called Cyclone Annotate, which gives you, this is just the same code as before. So this is the exact same code as the Python implementation, but when you run -a, you get this HTML output that Cyclone's telling you, okay, what code am I generating? And then these yellow lines are saying how much Python code does this line actually correspond to. So CS equals 0. It's like I know how to do that in C. I know what 0 is. That's fine. But defining a function, iterating through range n, these are all Python operations. And you can click the little plus, see this is the C code Cyclone is emitting. So in case you ever wondered what Cyclone actually looks like, it looks like this. It's just not the most understandable. But the gist is bigger is bad. So you want it to be small, and you want to just minimize that yellow. And so you look at the lines where there's yellow, and in general, with Cyclone, it's all about telling Cyclone about what you're giving it. So if you don't tell it anything, it has to assume this is an arbitrary Python object. you didn't tell me what n is. I have to be able to accept that n is a socket, IPython itself, a web browser, not a web browser, a web server, or a number or a string, imaginary, float. It can be anything. So you're saying, okay, range n, I don't know what that does because I don't know what n is, so I just have to take the Python object you gave me called n, and I have to give it to the Python built-in function called range. So the first thing I do is add this cdef. So this is saying, okay, this is a C variable. So I'm saying I is an integer. So then Cython can say, oh, okay, I and n are integers. Cython knows when you do I in range n with integers, I know what that means. I can actually make that C code instead of Python code. So if I expand for I in range n, this is just a C for loop, right? So that line that was huge is now 3 lines. It's saying variable for loop, you know. And then if we do it again, we say, okay, our sum should also be, so right now we've got, oh, okay, we've got something, we're doing a Python sum on CS because we don't know what that is. So CS is 0, we're doing these additions, but we haven't told it what CS should be. So if we run it again, we can see now we've got no yellow because we told it what CS is, we told it what I and N are. It knows how to do addition of integers, and it knows how to do iteration through a range of integers. So that means that Cython can take that information, generate pure C code, and then the only Python code is in calling the basically traversing the barrier of calling the function and returning the result. And then we can do some timings of our various implementations of this and see kind of how it performs. So the pure Python one takes about 100 milliseconds. Just generating it with Cython gets us almost half, gets us about 30% faster, just saying, hey, Cython, what can you do? And telling it nothing. And then we tell it a little bit more, and that doesn't help us too much until we get to the last one, where it's pure C, and we're now down to 100 nanoseconds from 100 milliseconds. So it's about 1 million times faster. And you can see that we didn't really make that jump until we got all the way to there's no Python code in here anymore. So now back to our actual problem at hand. So we're taking the Numpy version and then just saying, hey, Cython, I'm not going to tell you anything, but here's the Numpy version. What can you do? Okay, now it's worse. So just telling Cython, hey, it's Cython now, doesn't always win, right? So it's a little bit faster than the naive version, but it's a lot faster than the Numpy version. I'm not going to go into why because I don't fully understand it, but the important thing is that just telling Cython, just throwing things at Cython doesn't always help. Sometimes the simple pure Python Numpy version can be better if you're not going to put in the work to actually do Cython optimizations. So the next step is to tell Cython, so Cython understands NumPy. A lot of what Cython is for is working efficiently with NumPy arrays purely in C. So in addition to the Python import NumPy, I'm also importing a bunch of Cython headers about NumPy that basically say, when I work with NumPy arrays, Cython, do what you can. And that's the C import is making this, telling Cython to understand what NumPy is. And I'm saying, okay, steps is an integer, right? Because we started with this really yellow for loop. That's what we don't want. So we're defining our iterators and our range. So these can be. So now we've got the Python out of our iterations. That's important, but we've still got Python in our inner loop. And so that's really the key. So how much did that help? Not that much, right? So it's not actually iterating with, the iterations themselves are C, but the inner loop is still calling out to Python, and that's what we want to minimize. So the next step for optimizing Cython code with NumPy is to, so we told Cython it's a NumPy array, but we didn't tell it what was in the NumPy array, right? NumPy arrays can contain all kinds of stuff. They can be integers, they can be floats, they can be strings, they can be Python objects. So just telling it that it's a NumPy array isn't quite enough. We want to say this function actually takes a NumPy array where I'm going to tell you these are double precision floating point numbers, and it's a 1D array. So now Cython knows the shape of the dimensions of, it knows the shape of the shape. So it knows that it's a 1 by n matrix, or 1 by n array, and it knows that it's an array of doubles. So it can say, okay, when I'm operating on an element of this array, I can generate the C code for operating on doubles, because I know what I'm going to be given is an array of doubles. It's a little bit better. So now we can see, if we look back up here, this is real bright yellow on our inner line. And now we've told it what x and y are. And we can peek. So now, this is really the really packed in Cython version of the line. But if we look, all these lines are if the index is bigger than the shape, right? So these are all checking whether the iteration is outside the array. And because you don't, if you didn't have this, and then you asked for an element just outside the array, well, that's what's called a segmentation fault. You're asking for memory that you don't own. So in order to get nice Python errors instead of the process dying, Cython and Python in general says, before I ask for an element from this C array, make sure that I'm asking for an element that's going to be there, and if it's not there, raise a nice Python error message. However, since I wrote the code, and I know I don't write code with bugs, I write code that's always right, I can say, so we can see how that one did with types. That should help a little bit. Okay, now we're faster than NumPy. So just saying the types were faster than NumPy. But because of all that code on the bounds checking, and I know that I've actually asked for the shape, so I don't need to check again that the index is greater than the shape, because I'm actually, n is the size, and I'm going from 1 to n minus 1. I'm never going to ask for something outside the bounds. So I can say, hey, Cython, don't check for if I'm out of bounds. And then wraparound is dealing with negative indices, because I know I'm always going to do, I know 1 to n minus 1 is always positive. I'm saying, hey, Cython, trust me, I'm not going to cause any index errors. You don't need to check. Just trust me. I'm going to do it. It's okay. And so what that does is now it's just a bunch of temporary variables and then a single line of C code. So now there's no Python involved, no checking. And if I'd done this wrong, which is really easy to get wrong, like if I'd done this from 1 to n, this would segfault now, because I don't go from 1 to I go from 1 to I plus 1 because I need to ask for the right. So if I had done this slightly wrong, now this code would segfault, but that's on me. It's because Cython would have saved me. But now that I know it's correct, I can basically, after I'm sure it's correct, because I'm not getting those Python index errors, I can say, hey, Cython, now I'm sure that my code is correct. You can turn off those checks so that it's only going to, so that it can get rid of that little bit of Python code in the inner loop. And now my inner loop is all nice and clean, yellow free. So we can see how much does Cython help. So now we're at about 1 millisecond. So that's 1,000 times faster than our Python version and 10 or 20 times faster than NumPy. And you see, it's still doing the same. This is kind of a tour of how Cython and IPython and the notebook can kind of help you go through the optimization process of writing your code, seeing where the slow parts are with the Cython magics, and then iterating on that and improving on that, and running the timings to kind of compare, see how we're doing, see which changes are the most effective, and then plotting the results. And then we can take this, and the extra thing is, we just learned something about optimizing with Cython. We can save this notebook, and then where it is on GitHub, we can see just a record of what we did. We can share, and other people can see. Oh, okay. So now I can look at all that code, and I don't know why the annotate doesn't work well. I can go down the bottom and see, those results and share them with people to say, this is what, this is what I found when optimizing my code. See if that's useful to other people. So there's another tool. So we just did hand optimizing with Cython, which is often useful. Cython is also really nice for calling. So this let us take a Python library that happens to be written in C, NumPy, and optimize that with Cython. So it's basically taking Python code and making it faster with Cython. You can also use Cython for if you've got C libraries. Like if, let's say, you knew you had a C function that actually did this. Some C library did this smoothing. You could use Cython to say, just call that function on my array, and get similar performance things. So it can be used for both this kind of optimizing existing Python code, but it can also be used for calling out to C libraries. Numba is a library based on kind of more modern principles of optimization called just-in-time compilation. So just-in-time compilation is a way of taking code that you don't necessarily, you write the code and you don't necessarily know what the types are, so it starts out very slow with all these type checks, but then it says, when you call it, say, okay, you called it with this type, let me analyze the code, basically take the first call as type annotations, and say, okay, since you called me once with this kind of thing, generate the fast program for that type that removes all the type checking and everything, and does the fast version based on how you called it. It's basically letting the compiler say, make it fast, but do all the type inference at runtime instead of making me tell you, manually that this is a 1D array of doubles. You could say, if you call me with a 1D array of doubles, I'll see what I can do with that information. And so this is just our regular NumPy version, exactly the same, except it's decorated with this NumPy AutoJit. So AutoJit is just not NumPy, Numba. So Numba says, okay, I got a Python function, let me see what I can do with that. So Numba did better than everything other than our kind of hand-optimized best result. And all it did was take the single NumPy result and just add one line of Numba, make it fast. So there are a variety of tools. Numba can't JIT everything. This is a particularly good example where Numba does a good job. We could also apply the Numba JIT to our pure Python version and see how that goes. Yeah, actually might be interesting. Yeah, so there are a variety of tools for making things go fast. Cython lets you do it by hand, which can, if you you can do a better job than the automatic tools generally if you can put in the effort, but the automatic tools can often do a good enough job so that you don't actually have to put in the time unless you really, really need to optimize something. So the next piece, so we were timing the whole thing, and our profiling, we were optimizing our code to make our whole function go faster. Profiling is something that you do for figuring out why it's slow. So like I'm running something, it's taking 2 seconds, I want to make it go faster. Profiling lets you say, what part of the code should I focus on if I want to make this, if I want to do my optimization, where should I focus my attention? And with Cython, our profiling was really just the yellow. So we used yellow to say, I want to focus my attention on the yellow parts. Profiling is a more scientific approach to finding where in the code you should be focusing your attention if you want to be optimizing. So I'm going to write a simple script that just walks my temporary directory. And Python comes with a profiling module called cprofile. And if you run any Python script with python-m cprofile, you get information about where you spent your time running that code. And this is spending a lot of time just starting the Python interpreter and importing modules. Not super interesting. And then you can see the actual information here. At runtime, so that used the cprofile to run an entire script. Interactively, you can use cprofile, a cprofile function, and then pass it a string of Python code, and it will run that and profile it. And this will be the same information as above. It's just it won't include all the imports because I'm not timing the imports. I'm only timing the one line after I've already done the imports. So I can see that os.walk, or this putting os.walk into a list, is spending its time checking links, and it's getting the path separator, and then it's joining things into a list. And you can see these are the kind of where it's spending its time. But again, anytime that you're putting Python code as a string, that can be a bit tedious because you have to deal with things like escaping quotes. So like I had to make sure I used single quotes here because I've got double quotes out here. I could have done the same thing by using triple quotes. So this lets you, it's a bit inconvenient to write Python code in a string, not least of which is because we don't get syntax highlighting. I can't tell, if I had done that to, my parentheses are unbalanced, that kind of thing. It's a little harder to see that when you don't have syntax highlighting. So just like this, we have prun as a profile run. It's just like time it, except it profiles instead of times. This is really just the same as this. It's just in this magic syntax. So I ran that, and then sorted by calls. So we're calling scander, we're calling lstat. This is where we're spending our time. But this isn't the most informative structure of information in this table. Maybe I want to see, where you're spending your time, what's calling what. I want to see the call stack, show me the hierarchy. There's a tool called SnakeViz, and SnakeViz is a visualizer for the same information. So this kind of difficult to read table, I can run with Magic SnakeViz. What this does is it'll open up I gave it a longer job. It takes about 10 seconds so that there's bigger numbers to look at. What SnakeViz does is it runs that code, and then it produces this same table of information, I think. Yeah. And then it gives me, so this is the exact same information, but now I've got a call stack of, okay, this is just run some code. Okay, here's walk. Walk is spending most of its time calling isdir for some reason, and it's checking if things are links, and it's calling scander, and then you can show it as an icicle graph to kind of see the hierarchy of who's calling what, where is it spending your time. And so if this were your function, you could say, okay, I want to spend my time here. This is the information I'm after. And then this is the same table, but now I've got little sort buttons, and I can search for, okay, where's scan? Okay, there's scander, it's doing that. And I can go back and to my notebook and say, let's do snakeviz blur. What am I calling this with again? Next steps. So what's the profile of my Python thing? Oh, well, it looks like not a lot of useful information, because I'm just spending all my time in my function. An error occurred. Let's try the Numpy one. See if that gets it. Nope, not more useful. Yeah, it's just spending its time just in the function. Not the most interesting. So snakeviz can be useful depending on the nature of your code. I think it's because it's spending a lot of its time in the inner C code, which is not that interesting. Let's do, actually, yeah, so this is profiling the numpy dot product, which is almost all in a C function of dot, but then spending a little bit of time actually calling the function. So you'll be able to see, where are you crossing the boundary to C functions, because this profile won't go all the way into C functions. It will kind of stop at that layer. But you can see in NumPy, a lot of the functions are just like calling a C function on an array. Like that's what dot is. But then some of them are actually complex Python assemblies of things, and you'll be able to see, where am I spending my time, and why is this thing slow? You can see kind of what it's calling, and maybe this actually came up with a colleague at Simula. He found running the tests on a package was about 100 times slower on Python 3 than Python 2, and he's saying Python 3 is so slow. And then he ran a profile on the test, say, where am I spending my time? And it turns out where you're spending all of his time was running this basically deprecated method, a deprecated method for inspecting code that he realized he didn't have to run it very often. He could just cache the results, and by caching the results, the Python 3 test got about 1,000 times faster and an hour faster than Python 2, because he found, okay, I've got this hotspot in my code where I'm spending all my time, and I really don't need to be spending as much time as I am. I can cache results. There's an optimization called Memoization, which is basically telling functions to, if you're calling this function with an argument, remember the result, so that if I call the same function with the same arguments, instead of running it again, just return the result from last time. And this is useful if you've got what are called pure functions, so they don't have side effects, that running it multiple times shouldn't do anything different. But often you'll have things that, storing the results is inexpensive relative to recomputing, but from an API standpoint, you want to just be able to call it a bunch of times, that it can be useful to, and there are decorators in the Python language called LRU cache in the functools library that'll do memoization. You can decorate a function so that anytime it gets called with a new, anytime it gets called again with a given argument, it will just return the previous one rather than going through its whole function body again. And so memoizing your slow pieces, saying, I know what the result of that should be, don't do it again, can be a useful way to make your code faster. Yeah, I think that's about time. Any questions?
questions? So all the lectures are actually IPython notebooks. So you can download the lectures, for example, on the web page and run them on your own computer and execute the code statements